Şimdi geçen ders residue teoremi yapmıştık değil mi? Last time. Theorem. Residue. So what does this tell us? C compact Riemann surface. Omega bir tane meromorphic differential form. Then the sum of the residues of omega over all points is equal to 0. Okay, so bunu ispat ettiydik değil mi? Tamam. Şimdi bunun bir sonucu olarak teorem again compact Riemann surface, so I will just abbreviate like this. If f is a meromorphic function, is not a constant function, then the sum of, again, this time not the residues but the orders of f at all points is 0. Bunu söylemiştik ama ispat etmemiştik galiba, değil mi? Bu tabii nedir? Yani bu in this sum we have positive terms and negative terms. Positive terms corresponds to zeros, negative terms corresponds to pole. The sum is 0 means in particular the number of we have the number of zeros of f is equal to number of poles of f, of course counted with multiplicity. Yani şöyle diyeyim, zeros of f, number of zeros of f is equal to number of poles of f. Bu da residue teoremin bir sonucu olarak şey yapılabilir. Bunun hatta let omega be df over f, okay? So f is a meromorphic function. Just take its differential and then divide it by f. Then this is a meromorphic differential. Then and apply the residue theorem. Okay, the residues of omega will be just zeros and poles of f, and the sum is 0. Therefore, we will obtain that theorem. bunu yapalım mı? Şöyle isterseniz şöyle diyeyim. Yani diyelim ki bir noktada f'in zero'su olsun. If p is a zero of f, bir koordinat chartında olduğumuzu düşünelim. Then bu nokta civarında, then around p we may write f of z. Yani bu noktayı işte orijine taşıyalım vesaire. Bu nokta şöyle bir şey olacak. Bu madem zero'su var, bu işte bir şöyle bir sayı, pozitif bir sayı çarpı ne olacak? İşte bir tane gz, değil mi? Gz de sıfırda, özür dilerim, sıfırda sıfır değil. Burada şurada bir tane pozitif integer. Pozitif integer. Peki o zaman df over f ne olacak? So df is just nu times z to the power minus 1 gz plus z to the power gz g prime z, and you divide this by f. F is this. So when you divide by that, you get over z gz plus plus g prime z over gz. Okay. Şimdi G holomorfik bir fonksiyon yok. Evet, yani o nokta civarında holomorfik. Bunun sıfırı olabilir mi? Ha, olabilir. O beni ilgilendirmiyor. Ben bunun şu nesne holomorfik ve payda sıfır olmadığı için bunun sıfırda pole'u yok. So this has no poles since G0 is not zero. Yani burada şöyle bir şey yapıyoruz. Bu P noktasını orijine taşıdım. So I carried this point to zero origin and I have an open set like this. And this open set, on this open set, this function has no zeros, okay? Therefore, this function has no poles here, this ratio. Now, so what we see is then, so what is the integral of this over a circle? So what is the residue of omega at p? So you just integrate over this. This will not contribute. So what we will get, yani şöyle bir tane küçük çember boyunca. Şurada mı? Okay, okay. So this is gone. Yes. Okay, okay. I have only this. Now, if you just choose, buna da C demeyelim değil mi? Bir tane circle seçeyim. Let's say this is gamma p, integral over gamma p. So I have, of course, here I have, I forgot, but we have, of course, the whole thing is multiplied by dz, of course. So I have this dz over z plus this gadget but this thing is holomorphic on this disk. Therefore, this integral is 0. And if you compute this integral, it will be just what? Residue bunun 1/2 pi katı mıydı? Öyleydi. 1/2 pi katıydı. Şöyle 1/2 pi I. So if you just compute this integral, it will be, so this thing will give you 2 pi I, but you have 2 pi I over here in the denominator, so they will cancel out. So you will just get this. Let me actually call this P, okay? So what we see is then, if our function has a 0 of order nu P, then the residue of this differential form at this point is just the order of the 0, okay? Well, what about the poles? Diyelim ki bir de polu olsun. So similarly, if f of z has a pole at p of order nu p, then f of z, again, by carrying this point to the origin and opening the Laurent expansion of f at that point, we will get something like this. So z to the power nu p g z. And here this time, this thing is a negative number, okay? Negative number. So if you just do the same computation, everything will carry out. So omega, which is df over f, will be the same thing. So nu p over z plus, again, g prime over g, and then z. So when you integrate this again, similarly, we will get this residue of omega at p will be again just this number, okay? But this time it is a negative number, okay? And it is just the order of the negative of the order of the pole. So if you just add all these residues, so this thing is done. So I want to compute this, right? This thing. So this will be just this residues. So some of the residues of omega, but I know that the sum of the residues is just 0 by the residue theorem, where the last equality follows from the residue theorem. Again, we are using, of course, strongly some facts from complex calculus, namely, to compute the residues of a function, you just form that differential form omega df over f, and then you just integrate it, okay? Integrate over a small circle. Peki, bir tane corollary'miz var. Corollary. Şunun bir sesini kontrol edeyim de. Kim? Evet. Tamam. If f is a meromorphic function and is not a constant, is not a constant, then for any A in C complex plane, we have number of pre-images is just number of poles of F. Here, here, this thing is just is the number of pre-images of A under F. Yani şunu söylüyoruz. F complex plane'den complex plane'e bir fonksiyon, pardon complex plane'den değil, şeyden compact Riemann surface'ından. So it's a function from the Riemann surface. And I have a meromorphic function into the complex line. I just choose any point, okay, any point, and look at the pre-images of this point. So these are the, let's say, pre-images. P1, P2, P K, let's say. So F inverse of A is just P1 up to Pk. Counted with multiplicity. Okay, so actually, maybe this is a double point. Ne demek bu? Maybe around this point, the function takes that value twice. Like, you know, f of x equals x squared. So it's 0 is a 0 of this, but 0 is a double 0. Okay, so counted with multiplicity is the number of pre-images under F counted with multiplicity. How can we prove this? Proof? Well, just let replace let G to be by this function minus f of A, pardon, A. O zaman then G of Pi is just f of Pi minus A, but these are just A minus A. So the zeros of this function are just these points, counted again with multiplicity. What about the poles of this function? So, so this set, f inverse of A, is just number of zeros of G. But I know that for a meromorphic function, G is a meromorphic function because f is a meromorphic function. So this thing is the number of poles of G, but the poles of F and G are the same. Okay? Yani bunun sonsuz olduğu yerlerde bu da sonsuz. Başka da öyle bir nokta yok çünkü ikisinin arasındaki fark sonlu bir sayı. So this is just number of poles of F. So what we see, this number, şöyle yazayım. The number of preimages of A under F is equal to the poles of F. Yani bu da ne demek? Her noktanın böyle bir tane herhangi rastgele bir meromorfik fonksiyon alırsanız her noktanın preimagindeki sayılar aynı. Sonsuz dahil. Sonsuzdakiler de pollar. Right? So if you have a meromorphic function, the preimage of any point has the same number, including the point at infinity, which corresponds to number of poles. Değil mi? Yani sonsuz dediğiniz şey aslında yine bir preimage. Hangi noktanın? Sonsuzun preimage. Başka bir şey değil. Ha yok, bunu böyle yapıyorum. Öbür tarafı siliyorum. Bu sonucu zaten size daha önce ben aslında söylemiştim. Yani bu topolojik bir şeydir falan diye söylemiştim. Onu şimdi ispat etmiş olduk. Burada da demin söylediğimi söylüyorum. Remark regarding a meromorphic function f in Kc as a holomorphic map, a map f from C to CP1, right? Because any meromorphic function is just ratio of two polynomials. You just write those two polynomials side by side. So you get a function here. The above corollary yani şeyi yapıyoruz. Oradaki pollarda değeri sonsuza gidiyor ya. Sonsuzluğu da ekliyorum C'ye. CP1 elde ediyorum. Tamam mı? Başka bir şey değil yani. İsterseniz şöyle yazayım hatta. Değil mi? Bunun görüntüsü normalde C'nin içinde pardon şöyle C union sonsuz. Sonra ne diyeceğiz? The above corollary değil mi? Şöyle. The above corollary states that the function CP1'dan integer'lara giden fonksiyon, hatta yani pozitif integer'lara giden, şöyle diyeyim. Hangi fonksiyon? Herhangi bir P noktasını alıyorsunuz. Bunu number of F inverse of P. Kaç tane o noktanın ters görüntüsünde eleman var? P in CP1 olmak üzere is constant. Değil mi? Bir nokta veriyorsunuz. O noktanın inverse imajında kaç tane nokta var? Biz gösterdik ki bu fonksiyon constant. Tamam mı? Okay. Şimdi we'll start section 5. So more on differential forms. We already actually talked about differential forms, but this time we will study them in more detail, relating it to linear algebra and so on. Writing a complex number, any complex number, number z as x plus iy, we identify C with R2, and any map, any function f from C to C may be regarded as a mapping from R2 to R2. So it has real and imaginary parts. So f xy is just u xy, comma v xy. Biz genelde nasıl yazıyoruz? Bunu şöyle yazıyoruz tabii. U xy plus I vxy. But regarded as a point in R2, this is the, of course, correct way of writing it. Şimdi okay. Şimdi differentials first differentials on R2. Önce tangent vektörlerden bahsedeyim. Tangent vectors at a point P. So on R2, we so this is R2, and I am at a point P. Okay. So what's a tangent vector? Tangent vector is just a vector at this point. So this gadget is a tangent vector. This is another tangent vector, and so on. Okay. What are these tangent vectors? Actually, they are just directional derivatives. Okay. So this thing is just, we call it del x. And to indicate that this is a tangent vector at P, we sometimes write like this. And what's another tangent vector here? This is del y at P. Okay, so these are tangent vectors. And on R2, you know, the tangent space, the set of all vectors form a vector space, and it has dimension 2. So a tangent vector at a point P is regarded is is a directional derivative, is a direction along which we differentiate functions. Yani del x del x p bir tane fonksiyondaki değeri nedir? So this thing is just this is just del f del x at p. Okay. Similarly, what is del y at p of f? This is just del f del y evaluated at p. So this is the point where which indicates that you are at the point P. So you are taking directional derivative of f along this direction and compute that derivative at the point P. Okay? Yani şurada bir nokta olsa, if you choose a point here, okay, and you have this directional derivative here, this one is not equal to this one, okay, because this is derivative at the point Q, this is derivative at the point P. They are different objects. Another tangent vector, for example, is this 2 times del x del p minus 5 times del x del y p, right? This is another tangent vector. So what is, for example, v of p? So this is just 2 times the directional derivative of f along x at the point P minus 5 times directional derivative of f along y at the point P. Okay? All right, so that's the tangent vectors. The set of all these vectors clearly form a vector space, which we will call the tangent space at the point P. Okay, so let me just do that. Kitap tam benim gibi yapmıyor ama hani böylesi daha şey. The set of tangent vectors at the point P forms a vector space called the tangent space of C at the point P and denoted as TPC. Okay, TPC. Efendim? Real. Yani haklısın. Belki yani şey tabii burada şey çok önemli değil. Bunu böyle görüyorum. Şu anda real vector field, vector space olarak tangent space of uh, now we consider TP C or TP R2 as a real vector space. Dimension'ı tabii bunun nedir? Dimension as a real vector space of TP C or R2 is just 2, right? Because it has two basis vectors. Şeyi sorarsanız niye bütün hani directional derivatifler sadece iki tane yani base tarafından generate ediliyor? Belki böyle söyleyince ondan kurtulmuş oluyorum ama hani orada biraz sıkıntılı işler var. Onları halının altına attım şimdilik. Siz de görmediğiniz sürece sorun değil şimdilik. Peki, differential ne? Differential da bunların duali. The dual space, let's say TPR2 star of TPR2 is called the cotangent space of R2. So it is not tangent, but it is cotangent, okay? But at the point P. Remember that from linear algebra, if you are given a vector space, you can form its dual. And what is this? This is just the set of all linear maps, actually homomorphisms from V to R. Okay, V to R. If V is a finite dimensional, then these are isomorphic. But there is no canonical isomorphism, okay? So there is no canonical way from V to V star. But once you choose a basis, then you can form so-called dual basis, and that gives a isomorphism between these two. So if you have, let's say, a basis here, let's say, consisting of n elements, then we have so-called dual elements, dual basis, right? And remember how they were defined. They were defined like this. So the ith dual basis element at the jth basis vector has the value Kronecker delta ij. So V1 star takes the value 1 at the first basis element and 0 on the rest. V2 star takes the value 1 on the second basis element and it is 0 on the rest of the basis elements and so on. So that's the defining equation for the dual basis elements. And this way we obtain a isomorphism between a vector space and its dual, provided that V is finite dimensional. If it is infinite dimensional, then this is much bigger than this one, okay? Much bigger. Yani birisi mesela countable basis olur, öbürününki uncountable olur. Atıyor muyum? Peki. Şimdi bizim şeyimize dönelim. Here I have TP R2 and we have TP R2 star cotangent space. And here I have the basis del x, del over del x at P, del over del x, no, del y at P. And the corresponding vectors here, dual vectors, dx at P and dy at P. Okay, so what is this? Dx at this gadget. This is the dual element. So if you feed this covector with this vector, you get 1. And dxp del del yp is equal to 0. And del dyp del del x p is 0. And dyp del del yp is 1. What if I choose a different point here? Well, then they are unrelated. Okay, you cannot relate tangent vectors at a point with the covectors at some other point. Okay, they are unrelated. So, for example, consider the sphere. At this point, I have a tangent space. Its dual space is again at this point. Here I have another tangent space. The dual vectors of this tangent space again are at this point. You cannot relate tangent vectors at this point and at this point and covectors at these 2 points. Well, actually, I am lying. You may relate them, but it's another story. Okay. Efendim? Yeah, you can push them, you can carry them, but it is not usually canonical, but there are ways of doing it canonically. So it's actually a subject in differential geometry. Hangisinden? Örnekten fazlasını yapacağız. Bundan sonra hep bunlarla uğraşacağız. O yüzden şey. Şimdi peki şeye bakalım. Zamanın var mı? Bitti mi? 6 dakika. Okay. So okay. Now, what about complex with complex variables? Since z is x plus iy, okay, we will write the differential of this dz as dx plus I times dy. Okay. Of course, one has to be actually careful that this is at a point, this is at a point, and this is at a point. Okay. What about the tangent vectors? Well, del z p. So what is this? Z is this, but what is this gadget? Of course, here we have also the following. What is z bar? Z bar is just x minus iy, and dz bar will be just dx minus I times dy. You may take these as definitions if you like. Okay. Now, what is this gadget and this gadget. Okay. Well, you see, these two, DZP and DZP bar, let me just add this up. So when you do that, this imaginary part disappears and we have this. Therefore, dxp is just 1/2 times dzp plus dzp bar. And what about dyp? Well, to obtain that one has to subtract this gadget from this gadget. So dxp's will be cancelled, and I will have 2 times I times dyp. Therefore, it is just 1/2 times dzp minus dzp bar. Okay. And then we can haklısın. There's also I here too. So we wonder what are these gadgets, and let me just do it in the second hour. Ara verelim.